Okay, so what we've got today here is a scenario where we are going to find out how to maximize the volume of a box, tying into problems that we've been doing with polynomial equations and finding relative mins and relative maxes. So let's see what the scenarios that we have. All right, we're going to make an open rectangular box out of a 4 by 12 piece of metal. The box is going to be formed by making cuts of equal lengths in each corner of the paper and then folding those sides up. You want this box to have the greatest volume possible. Let's look at what that might mean. Got 3 different scenarios. In the first box, looks like they just cut out little corners on each. When they fold up those flaps, it makes a box, holds a little bit. In the second scenario, what they've cut out is a little bit bigger in each corner. And it looks like the box may hold a little bit more. Third scenario, even bigger cuts still. But surely we would not be able to just keep cutting out and still make the box hold more and more and more. Eventually we would get to a point to where the cuts would be so big we wouldn't have a box to build at all. So what our job is going to be is to find out that perfect situation, that perfect length cut, which we're going to call X, so we can make this box to hold the absolute most. Let me show you a different way of looking at this using Geometry Sketchpad. This rectangle represents our piece of paper. The yellow in each corner represents the cuts that we're going to make. Okay, we'd cut in a little bit here and a little bit here and cut out that so we could fold up this box. Well, look down here at my equation, length times width times height. That's volume. It's showing it in cubic centimeters. Okay, well, if I make tiny little cuts, look at my volume. It's down here to like 38.5 centimeters cubed. If I make that cut a little bit bigger, we're now up to a little bit better than 50 cubic centimeters. Make that cut a little bit bigger, we're now better than 60. Is it just going to keep going up and up and up and up and up? Well, we're going to get to a certain point. Well, uh-oh, look what's happening. Volume's coming back down now because we've passed that point where the cut gives us the maximum volume. So our job is going to be to come up with an equation, and then we're actually going to graph it on our graphing calculators to see where this maximum occurs. So let's go back and take a look at our work, and here's what's going to happen. I've just drawn a rectangle to represent my piece of paper, and I believe in our problem it said that it was going to be 12 inches by 4 inches. So I've got that marked on there. Each one of the cuts in the corner is going to be the same length, so we're going to call those X in each corner. Now, we've got to have an equation to work with. We know the volume formula for a box. Volume equals length times width times height. Well, let's see what we know. Our length of the paper is 12, but once we make those cuts, the length of our box is only going to be that highlighted segment. And that's no longer 12 because we're taking away this little bit here and this little bit here. So it's going to be 12 minus 2x. So I'm going to replace my L with 12 minus 2x, an expression in terms of x. We're going to do the same thing for the width. My width is now going to be this length. It's not 4, but of course it is 4 minus 2x. And my height is just simply going to be x, the length of the cut, once I get those flaps folded up. Now, if you think about this, that's three different factors, each with a variable of x to the first degree. So that is actually a third degree equation, which we know by studying polynomial functions, but it's going to be a graph that looks something like this. We're just going to graph part of it. Perhaps it'll be maybe something like from here to here. And we're really interested to find out where that relative max is, and that's going to tell us about our maximum volume. So grab your graphing calculator and let's see if we can let our calculator help us. We're going to enter that equation into our graphing calculator under y sub 1 under the graphing. Okay, so I have my calculator cleared out, and here we go. We're going to enter 12 minus 2x close parentheses times 4 minus 2x times x. If you just do Zoom 6 and do a standard graph, it doesn't help you very much. So let's go back and think about what our window should be based on our drawing. We know that our x value, our cut, can't be a negative number. So the minimum that it could be would be 0. And that wouldn't be much of a cut, would it? We know we could not cut farther than halfway in. If we cut that, that would be a big square out and a big square out. That wouldn't make as much of a box. So we know we can't cut as far as even 2 inches. So I'm going to go back to my calculator, go to my window, make my x min be 0, my x max be 2, because that's as big of a cut as I could possibly make. I'm going to even change my x scale to where it gives me a nice little picture, maybe 0.25. Now let's look at the graph. I still can't see all of it at the top, so I'm going to expand my y max, go back to my window. Try my y max maybe at 30. Graph again. Now I've got a nice graph to look at. Now remember, this is showing the volume as it's increasing and then decreasing, just like we looked at a minute ago on the GSP sketch. We're increasing and then we're decreasing. We want to know what that maximum point is. So we use our calculate menu. So go to second trace, maximum. We've done this before. Move that cursor a little bit to the left of where you think that maximum is. And press enter. Do the same thing on the right bound. Press enter. One more time, and it tells us that our maximum is approximately 0.9. Remember now, that's the length of my cut, and 20.2 if we round it to the nearest tenth for our volume. So let's go back to our work again. We found x to be approximately 0.9. That's going to be in inches. That's the length of my cut. And my y value to be approximately 20.2, which would be inches cubed, because that's my volume. Okay, I believe we found everything that we needed with the exception of the actual dimensions. The problem asked us to find the length, the width, the length. If you go back up to our expression, is 12 minus 2x. And so if we plug in the value or substitute the value of 0.9, you can easily find the length. Same thing for the width. Our expression was 4 minus 2x. And so you can substitute that value of x in. And our height, of course, would have been just value of x, which is approximately 0.9. So we've looked at one simple way by using some drawing and our graphing calculators to find the maximum volume of a box. Now, in a little while, when you're chatting with your classmates, I want you to think about some real-life applications. Why would you want to maximize the volume of a box?